So we'll come back to that. Right? So complex 3, as the electrons are transferred, again, protons are transferred out. Don't worry about the stoichiometries on this slide. We'll come back to that. Right? And then in complex 4, again, you have proton pumping. Okay. What happens to all these protons? Here they come back in, right here. This is ATP synthase here on the right. Okay, this orange guy. It has two subunits, FO and F1. This is the matrix here. Right? As the protons come in, obviously this is downhill. It's going plus to minus with protons. And so that drives the synthesis. Okay. Yeah.
I might just be missing something, but on the first complex we have Q, and that gets reduced to QH2. And then on the second, so does another molecule Q come in? Or
Yeah, there's a whole pool of Qs in the membrane.
Okay.
Yeah, I mean, there's Qs all over the place in this membrane.
Okay.
And so when electrons come up through these proteins, they get transferred to a whole bunch of chains. This blue is hiding a lot of detail,
Okay.
right? And so eventually it gets to Q in both cases. Then it helps create a pool of reduced Q.
So you actually have two Q going into complex 3.
You do actually have two Q. You actually two Q binding sites on complex 3, which we will see. Yes, sir.
You know if there's any channeling going on, it's like are we designed adjacent?
Yeah, certainly 3 and 4 are together. It's called a respirosome. I think I had that on a later slide. I don't think that there's, that's why Q is diffusible in part because there's not direct complex formation, at least not in a way that easily makes it possible to move the electron equivalents, the reducing equivalents across. Yeah. Any other questions? All right, so we'll come back to this again and again. All right. So if we step out a little bit more broadly here, right? This is just the first two complexes, okay? But what's broader is that we're also bringing in electrons from other places, right? So here is beta oxidation. Acyl-CoA dehydrogenase, you may recall, is the enzyme that puts the double bond in. The first oxidation step on a reduced fatty acid puts in the double bond, and that process makes FADH2, right? The first beta oxidation step, which is equivalent, of course, to the succinate step in the TCA cycle. Remember that three-step sequence, which is equivalent in beta oxidation, the last 3 steps in the TCA cycle. Right? Well, here's that step, and here's the TCA cycle. Here's the beta oxidation. ETF is electron transferring flavoprotein, just a general name for proteins that have flavins on them. And so here you see FAD becomes FADH2. It's not diffusible, but the protein that it's on is diffusible. And so it docks with another protein that has FAD, and so electrons transfer this FAD. It's thermodynamically favorable, even though it's FAD and FAD, because the microenvironment in the active site is a little different. So it's favorable to go this way. And then here's another one, electron transferring flavoprotein, Q oxidoreductase. Right? Another redox protein. This one also has an iron sulfur center as well as an FAD. Electrons go through and they get to Q. Right? And then they contribute to the pool of reduced Q in the inner mitochondrial membrane. So this is beta oxidation doing its thing and contributing to Q, the reduced Q pool. Right? Here is the glycerol backbone of the fatty acid, which did not get in the mitochondria, remember? It's a glycerol backbone of a fat, I should say, a triacylglycerol. Did not get in the mitochondria, only the fatty acid did. Right? And yet we had a slide before where we talked about the cell not wanting to use up, not wanting to waste the power of the glycerol. Right? Well, glycerol 3-phosphate dehydrogenase oxidizes glycerol 3-phosphate, produces FADH2. Again, electrons go to QH2. And later on, we'll talk about the electrons from the glycolytic NADH, the one from glycolysis, which is not on this slide. All right, so QH2 pool, complex 1, all the NADH from all the different processes. right? Here it is from the TCA cycle. Here's beta oxidation. Here's the glycerol backbone. That's 4 sources of QH2.
How was glycerol phosphate again, since it is the systolic side, but that's the membrane?
How does it get in there?
Yeah.
Well, it's diffusible through the outer membrane,
Oh, okay.
right? And then this enzyme here is associated with, if not, probably not an integral protein, but at least an associated protein with the inner membrane, but it's coming from the other side. Right? This is coming from the cytosol. This is the P side. So if something's going on in the cytosol, it got through the outer membrane here, came through, and now it's delivering in through here. Right? But those equivalents, right, can never come in through here. And you have to come in through here in order to generate that proton gradient. And you cannot come in through here and generate the proton gradient because you're topologically completely on the wrong side. There's no mechanism to do it that way. Right? So you cannot, if you could do that, then there wouldn't be a 30 versus 32 problem with the glycolytic NADH, because NADH from glycolysis, you could say, well, it's just coming through here. Right? But you can't. NADH can only come in through here. Does that make sense? We'll talk about that more. All right, so I'm showing this slide because it's hopefully good for tying in together some aspects of lipid metabolism where everything had to make, we're gonna make ATP from that too, right? Yeah?
Does beta oxidation contribute to the proton gradient in any way?
Yeah.
Okay.
Yeah, anything that makes QH2 contributes to the proton gradient because later steps, here, QH2 comes in here, all that contribution is up here. It all contributes to this. Here's QH2 coming in here, and now this part is all the same, no matter what the original source was. Right? So you're going to get at least this much from anything. It's just that you also get this. Right? You can if you're NADH coming from the inside, but not in any other case. Yes, sir.
So with the new contribution of the electrons from beta oxidation, is there some different way to quantify the amount of ATP that you get out of just beta oxidizing it?
Yeah,
Okay.
we did that in fact when we talked about beta oxidation generating one NADH and one FADH2. The NADH that we generate is here, right, generating more proton power, and the FADH2 is here. So any NADH made inside the mitochondria, no matter what the oxidation reaction, right, gets to come up through here. And therefore gets to generate this extra pumping power. Okay?
And that's per one NADH molecule, right?
Yeah, this is per pair of electrons. Yeah.
Have you showed us any examples where it's just the one electron transfer of Q yet?
No. Okay. Complex 1, also known as NADH ubiquinol oxidoreductase, the name you can immediately forget if you like. As long as you know that it starts with NADH and ends with Q. Is a proton pump driven by the energy of electron transfer. Right? That's what we've been saying. That we have downhill electron transfer, and we harness it immediately while it's transferring. We use that. If you want to ask how we use it, right? That's what. Well, there's a lot of research that's still going on into. Right? But we do. We apparently use it to generate a proton gradient across the inner mitochondrial membrane. Right? And depending on how much electron, the electron flux will generate a greater flux of proton gradient. So if there's more of these complexes or they're functioning more efficiently, then you'll have more of a proton gradient set up. So we can look at this guy and see what's going on in a little bit more detail.